Hey, good afternoon, everybody. Welcome to our webinar. And I'm Rick Klassen.
I'm Perry Thiessen.
And we are pleased to be with you this afternoon. And we have a little bit we'd like to talk about, just some new experiences that we're having here. Just very quickly, just a little bit about us. So we're with Klassen Advanced Filtration. And yes, my name is Rick Klassen. That's no coincidence. My father started our company in the 90s, and we're out here in BC, and we've been handling the CC Jensen line of filtration product since 1993, and we presently serve all segments of Canada with this product, and so covering industries including mining, power, marine, and oil and gas as well. So CC Jensen is the one line of product that we carry and distribute, and they are based in Denmark, and all the product is still currently manufactured there, and that's where their headquarters is. They have distribution and subsidiaries in many parts of the world, and we have quite a close-knit network, and we're able to utilize a lot of that knowledge and experience from other parts of the world and bring that to Canada here, and vice versa. A lot of what we learn in Canada gets shared to other parts of the world. So that's a great collaborative team that we're a part of.
Yeah, I was going to mention too, just as a matter of housekeeping, if people do have questions or comments, please make a note of that. We will have kind of a discussion at the end, and we do want to hear your comments and feedback and have some conversation, so feel free to make note of that, and then we can kind of open it up at the end and have more of a conversation. So we're looking at specifically the G3600 series of engines, but kind of looking to the past at kind of where this started. The first CAT engine ever made was below 100 horsepower. So if you think, currently with a G3616, it's over 5,000 horsepower. So it's a significant development in technology, finer tolerances, and ultimately just a greater demand that's being put on the oil. So that's kind of the comparison we wanted to make. And all of this development of technology, we're creating a significantly greater demand on the oil and just pushing it harder.
One more thing I'll note is that we are recording this webinar. So if you know others who weren't able to make it, or you'd like to share it afterwards, you will get a link to that afterwards. So.
Yeah, and we're obviously talking about natural gas in this application, but there is a silver lining in the sense that natural gas burns so much cleaner. In working with CC Jensen, a lot of what we've done in the past is filtration for the marine diesel engines, and there's a lot of difficulties associated with trying to filter the lube oil on diesel engines just because of how it burns. There's a lot of soot loading in the lube oil, and just cleaning up that soot is very difficult. So even with effective filtration, you're not going to restore the clarity of the oil. In this case, because natural gas burns so clean, we actually have an opportunity to restore some of the clarity in the oil, which is traditionally very difficult with engine oil. And we're actually able to track the particle count and reduce the particle count. Usually for diesel engines, doing oil analysis, we don't even track particle count because it's very hard to get a particle count because of the soot. And it's just not a parameter that's worth tracking because of the high levels of contamination. So burning on a relatively, like a clean fuel like natural gas that burns clean, we have an opportunity to actually recover and maintain the lube oil in a way that's not always possible when you're burning diesel. Yeah, just kind of the background more specifically, zooming into the Canadian market and the pipeline and the Grande Prairie and greater region of what's going on here. Kind of seeing a lot of issues being reported from end users. So specifically on the G3600 series, a major issue is the early hour oil filter plugging of the CAT OEM filters. And then as far as running with contaminated oil in the lube system, bore polishing is an ongoing issue, decreased oil lifetime, premature oil drains, also seeing bearing wear, sticking exhaust valves, intake valve recessions, and elevated emissions. So some of these problems are going to be directly related to excessive small particulate, and these are the issues that we're looking to remedy through effective filtration.
Yeah, and I'll say that while the principles of what we're doing here have never really changed, what we have seen is a sudden increase of the severity of these problems, and that seems to be related specifically to, or maybe have manifested itself greater in the Atom 4 generation of engines, and maybe it's not entirely certain why, but the Atom 4 is developed to run on a broader range of fuel, so from a lower BTU to a higher BTU rating than the previous range of the Atom 3. And it seems like the operational parameters of the engine have been adjusted to compensate for that broader range of fuel quality. And as a result, it's putting higher contamination load into the sump and causing more of these problems to show up. So the Atom 4 seems to have increased the awareness of this issue, even though a lot of these things have been happening on gas engines for many years in the past. It's just that they're showing up so much more now, which is why the increased focus at the moment. The ultimate thing that this results in is a great expense to the operators. So when an engine is failing, there's not just the cost of the parts and the labor to repair it, but there's the cost of the production downtime. There's the access. Often these are in remote areas, which are hard to get to. There's parts delays. All these things contribute to make a massive expense to the operator. And the total risk exposure that we've heard from the operators out there is these failures can cost over $3 million. And what we're ultimately trying to do is reduce or prevent those failures from happening, and extending the lifetime of the engine so that the components can run reliably, doing the job that they're intended to do.
Yeah, and kind of zooming out in terms of what does the oil actually supposed to do, or what is oil supposed to do in terms of acting effectively. So kind of the obvious one that everyone thinks about is it's a lubricant. So of course the oil is a lubricant, but it also has other functions that it's performing in systems, specifically in these engines. So it has a cooling effect. And then the oil also acts to protect the surfaces. So the oil film protects the surfaces from corrosion. And then it also acts as a seal for the piston ring. And it also has a very important role to clean. So the engine oils are part of the composition contains detergents to kind of move through the system and clean. And then also the oil acts as a cleaning agent as it's holding contaminants in suspension and then also transporting those contaminants, bringing them to the filter. So there's a variety of roles that oil is fulfilling. It's not just plain lubrication. So it's doing a lot of things. And as contamination increases, it's mitigating the effectiveness of all of these roles.
So one of the ways, as we mentioned, that this is showing up is in premature filter plugging, and the contaminant load in the oil is exceeding the capacity of the filters to remove the contaminants, both in pore size but also in capacity. So the finer particulate will often pass through the system filters, whereas the capacity of the filter can also be used up and basically block off the passage of oil through the filter, and that can cause either the filter to go in bypass, or even in severe cases, oil starvation to critical passages. And as the particulate load increases, it will also tend to stick to areas in the engine. So obviously it may settle in the sump, but also areas of low turbulence, which can be, machining passageways, things like that, where it can actually trap and hold particles and increase the amount of sludge deposits in the engine, not just in the sump. And one of the spin-on effects of that is having increased contamination in the oil as it's intended to lubricate the moving and sliding surfaces will lead to increased wear. So when you have contaminants going with the oil that's meant to lubricate the piston ring sliding up and down the cylinder, you get this harsh abrasive wear, and it's essentially sanding down the surface of the cylinder liner and polishing that surface. Now, the cylinder liner is intended to have some texture in order to hold that oil film and make sure that the surfaces are properly lubricated. So if that gets sanded down, eventually it's going to be a very smooth surface that not even the oil wants to stick to. And then you get this metal to metal contact, and that creates lines and scoring in the cylinder liner, and that creates passageways for the oil to slip down. So either drawn into the combustion chamber, also lets combustion particles pass from the combustion chamber past the piston rings into the crankcase. So and this is a problem that accelerates. It just breeds a faster degradation of the oil quality over time.
Yeah, and this is something we'll get into a little bit more later, but talking about the potential benefits of effective filtration on new engines versus old engines. If an engine's old and it's already experienced all this wear, we can't put metal pieces back onto those components. But what we can do is put an effective filter on a brand new engine and mitigate some of that wear. So that's something we'll discuss a bit more later, but kind of comparing the benefits of filtering on a brand new engine versus trying to kind of help an old engine hobble along when there's already these issues that have happened.
One thing that's also been noticed is that there's a bit of a discrepancy between the number of filters and the amount of oil per engine size, so per number of cylinders. So as the engines increase from a 3606 up to a 3616, there's a disproportionate shift, or a disproportionate increase in the oil volume, and actually the number of filters doesn't change. So it also seems to be made worse by the specific filtration and oil capacity per cylinder count. So from the 6-cylinder up to the 16-cylinder, they all just have 6 filters fitted to the engine from the factory, and the sump size does not increase proportionally. It's somewhat larger, but not relative to the increase in displacement and horsepower. So we'll talk now just a little bit more about the contaminants themselves. We know that oil does get contaminated, and this happens not just in engines, but in all other types of machinery where oil is in use. So we'll just kind of run through the basics of what those are and why it matters. So these are primarily the contaminants that we're concerned about in engines, as well as many other oil systems. We're looking at solid particles, water, oxidation products, and acids. And those cause a variety of problems in a variety of different ways. they tend to also catalyze each other in a variety of ways too. So the presence of one can increase the onset of another. Particles can come from lots of different places, even from delivery of new oil. Sometimes it's not handled very well, and maybe transferring from truck to drum to whatever. There's lots of opportunity for contamination through the atmosphere. And then also, as the oil is in use, there's always some wear component that's coming into the oil. And a lot of people are just careless too with handling. A lot of the particles that are really doing the damage are smaller than we can see. So people aren't always paying attention. They think that keeping the chunks out is good enough without realizing a dusty environment is also dangerous. Same with water, can come in lots of different ways. Primarily, we see it as condensation, especially in climates where we have extreme temperature swings, like Alberta. You can have some big effect from condensation there. Can also show up from things like cooler leaks, again, oil drums being stored outside, that sort of thing. Water is a terrible lubricant in machinery, and so we often see some very rapid degradation of components when high amounts of water are present. Oxidation is, there's a bit more to it. Often heat is one of the biggest contributing factors, but also air entrainment or introduction if there's a lot of oxygen coming into the oil, and it's a chemical breakdown of the oil in the presence of heat and contaminants, and what you see happening there is the oil can become tacky. We talk about varnish. So coating to interior walls of the oil system, and we can see some effects of that in the engines, and it can also occur from things like microdieseling. So that's the explosion of tiny air bubbles when they're exposed to high pressure. They heat up and essentially burn the oil around them. So again, lots of problems that show up as a result of oxidation. As I mentioned, we're talking about very fine particles here, and the smallest particle we can see with our naked eye is about 40 micron. When I had hair, the diameter of a human hair is between 40 and 80, just to give you an idea of how small we're talking here. When you're getting down to the very fine particles, that's where it becomes very critical to keep those particles out, because it's approaching the lubrication film thickness of these various components. And so we're talking a range that's much, much smaller than is visible to the eye. What you see can't hurt you doesn't apply here. And the reason why those particles are so damaging is that if they can enter the lubrication film thickness, that's the thin layer of oil that's meant to separate two metal surfaces. When they get in between there, it's like sliding down a slide at the playground that's covered in sand. You're going to feel that abrasion between you and the other surface, and it's no different with your bearings, with your cylinder liners. Those particles get between those surfaces and just cause damage as they go through. Often those particles will break down into smaller particles and increase overall the number of particles in the system.
Yeah, and just similar kind of talking about modern machinery with such fine tolerances. So previously in the past, when machines weren't designed so precisely, the tolerances were much larger, but now that there's so much power and efficiency being engineered into everything, those tolerances are very fine, and that's where small particles become even bigger of a problem, because the oil film thickness and openings where those small particles enter and cause abrasive wear are very small. So even the 5 micron particles and 3 micron particles, those are the ones that are entering the film thickness and causing that abrasive wear.
So one of the ways that we measure the number of contaminants, especially solid particles in the oil, is with something we call the isocode, and it's a scale, a measuring scale that's been developed just to help visualize more easily the kind of contamination and the quantity that you have in the oil. So it's a code devising of 3 numbers with slashes in between, and the range is in 4, 6, and 14 microns. If you see just 2, as often some labs will still just measure in 2 isocodes, it's always referring to the 6 and the 14 micron. And what it is it's a range of particles per milliliter. It's also, you can kind of estimate it based on the visual aspect of the oil. You know, a very clean oil is generally going to look clear. You can see through it. And as you get dirtier and dirtier, you know, sometimes you can even see large particles in the oil, which is an indication that there's many more very small particles. And basically, the important thing to know is that each movement on the isocode scale is a halving or a doubling of the number of particles. So if you go from a 20 ISO 20, which is between 5 and 10,000 particles per milliliter, to a 19, the number of particles is reduced to half. So that actually puts you to the range of 2,500 to 5,000. So each step down the isocode scale is half the number of particles. So sometimes you might see a change of 2 or 3 isocodes and think it's insignificant, but it's actually 2 times 2 times 2. So, you know, 8 times cleaner than you were before. And of course, the other way around also applies, that if you see it going up a number of isocodes, your oil is twice as dirty, twice as dirty, twice as dirty. So just an important thing to know about the isocode scale. Again, about the lubrication film thickness, these are just some figures of sort of accepted ranges of what that lubrication film thickness is in various components. So you can see here in engines with rings and cylinders, it's in the 0.3 to 7 micron range. So kind of right in that range that we're talking about with these particular filters.
And I think it's relevant. I believe even the KAF high efficiency filters are rated to about 15 to 20 micron. So, you know, being a full flow filter, you know, they're designed to allow a lot of flow come through to service the engine. But, you know, in this whole discussion of oil film thickness, if you're filtering 15 to 20 micron, you're letting through a lot of those particles that are below 15 micron, which in this, as this shows, that's where the oil film thickness is. So you're going to have a lot of small particles floating around in the lube oil, getting in those film thicknesses and causing wear in the liners and throughout.
When we're looking at the isocode scale, something useful that has been developed out of that is an estimation of life extension based on a change in the isocode. So this is a scale that was actually, or a table that was developed using real data from the field and comparing different cleanliness levels of systems and assessing the life extension achieved from that. So you can see in this example here, if your existing system was a 21-19-16, and through prevention or filtration, you reduce that to an 18-16-13, so a 3 isocode difference, you could expect a life extension of 2, so double the life of that component just by lowering the isocode by 3 isocodes. So just a useful tool to be able to estimate the impact of making a difference to your system. So we'll talk a little bit about the system that we have been using on these engines. So first we'll just describe what it is and how it works, and then we'll get into some of the data that we've collected from the engines.
Yeah, so we kind of alluded to before with the KAF filters, they're a full flow filter in line. What we're working with and supplying is a kidney loop configuration. So we're not full flow or in line. We're really just trying to take some of that oil volume through our own pump and motor, pass it through the filter media, and then return it to the system. So we're not in line with the system. We're just taking some of the oil volume, cleaning it, and then returning it to the system. So by using this kidney loop configuration, we have the luxury of not requiring high flow rate. So by design, our flow rate is very slow, and we want to pass it through the filter media and focused on high efficiency without any requirement to move the oil quickly. And then we also, as part of that kidney loop configuration, the filter unit can be serviced even while the engine's running. So if the engine's running, you can isolate the filter unit, change the inserts, inspect the inserts, or whatever you need to do with it. And then some key components to look at here is there's a differential pressure gauge on the top of the housing. So that would be the main indicator for when the filters are loaded and need to be changed. In these applications, it's usually about every 6 months is kind of been where we've been looking, but obviously that depends on how much dirt's in the system loading the inserts. And then another key feature is the relief valve inside the pump. So it's not a lot of filters will have a bypass. We're not bypassing any oil. But when the filters are full, or if there's any restriction on the outlet, then the relief valve will engage and the pump will just recirculate within itself. Probably also a good time to mention it's a very low flow, low pressure system. So we're not pumping at high speeds. It's operating pressure is between 1 and 2 bars. So it's a low pressure system that way. And then just some basic features of this unit. So this is the sizing and specification we've used for the G3600 series. And within that filter housing, there's 4 elements. Each of those elements will hold about 12 pounds of contamination each. So with a set of 4 inserts, you have a capacity of about 48 pounds of solid contamination, oxidation, all of those things. So you have a lot of holding capacity to kind of mitigate the varnish oxidation particles that are constantly entering the lube oil. And then very importantly, it also filters down to 3 micron absolute. So yeah, this wasn't something that we started here in North America. There's a lot of history with filtering on diesel engines, as we mentioned, but also the natural gas engines. So MWM, CC Jensen has an OEM agreement with MWM in Germany, which is also a Caterpillar-owned company. So all of these new engines that are put to the field come equipped with a CC Jensen filter. You can see it highlighted there on the bottom left. So we're kind of bringing to the North American market what was already started in Europe with the OEM there in years past. And just a basic overview of the spec. So like I mentioned, a very low flow rate. We're not trying to keep up with the engine demand for oil. We're just doing a slow kidney loop polish of the oil. So 240 liters an hour. And then we can operate with single phase 120 volts. And then the units are of course compliant for the Class 1 Div 2 environments, which most of these gas plants of course will be. And then we also have some options for if power is not available, we do have some options for addressing that as well.
So some of the results that we collected, one of the first tests that we did was a bit of a controlled group test with we had 2 engines that we fitted with the CJC filters and one that had none, and so we were able to track them quite closely, getting some samples off of those, and these are just some tests that were done in-house here. So patch test across the top, that's a 0.45 micron patch. So capturing those very fine particles. And then the test tubes there is the samples were spun through a centrifuge. And we can see the amount of debris that's settled. So the comparison of the two engines on the outsides, both of them were started with relatively new oil. The one on the left was brand new. You can see the kind of the reference sample there. The first sample we had on the engine far right was at about 285 hours. So you can see the hours kind of climbing before then. The last sample on, or the first sample on the middle engine was just before an oil change. So you can kind of see how much debris had settled and accumulated in that oil. And then the subsequent samples after that. And I put X's on two of those patches there, and the reason for that is the patch plugged up instantly with the test, and so no more oil was able to pass through. And I can only surmise that it was the ultrafine particulate that just plugged the patch off. The second and the fourth patches there on that middle engine, those did have the full amount of oil pass through it, so you can see how much darker that is. That's just why it looks a little bit misleading there. But you can see just in the clarity of the oil and the color, how the engines with the CJC unit were able to maintain some of that color to the oil, even through the first 2,000-3,000 hours of operation. Whereas the engine without is just dark kind of throughout, in a lot of deposits in the oil already, even by the 2,000 hours. So we've collected a fair bit of data off of these engines, and this is just a plot of engine oil hours and the 4 micron particle counts over those hours. So just a visual way to kind of see the impact that the CJC, the kidney loop system, is having on the oil. So even comparing the median oil samples, the particle counts on those two sets, the units with just the OEM filters are about 90,000, 91,000 particles of the 4 micron size. And the ones with the CJC units are running in about 7,700 particles per milliliter. And what you can also see is we're already stretching out the hours on these engines. You can see like the last data points there before 8,000, and actually those two engines now are almost at just before, or 8,800 hours and 9,060 hours on the same oil. So we're already seeing some impact on extended oil drains as a result of keeping the oil cleaner for longer. Unfortunately, those last two samples, they didn't collect the particle count information. We just know that they're still running the same oil, and as it is, the rest of the specs of the oil, the viscosity, the TBM, everything else seems to be still in check. So still running those oils out. So this is one operator, and we have collected some data from another operator, which looks a little bit different. Now, our understanding is that, well, for one, this is the 3616 engines. So they tend to run a little dirtier from what we've seen than the smaller displacement. But still, you can also see, even with this smaller data set, a massive shift between the units with, and these had some different type of filtration versus the units that have CJC equipped. So quite a shift in the particle count. And as we've already learned, the particle count, the particle contamination is a significant contributing factor to the wear on the bearings and the cylinder liners.
Yeah, just a note on this. Obviously, for the 4 micron, we do want to see oil cleaner than 78,000 or beyond 70,000 4-micron particles. But it's just relative to what's going on in the engine. So by having the CC Jensen unit equipped, we can still dramatically remove and reduce the overall particle contamination. It's not where we want to be in terms of cleanliness, but it's still a lot cleaner than it was without the CC Jensen filter. Yeah, so this is just a basic overview and design of the filter media that we're using. So as you can see, it's quite a bit different than the CAT filters that are equipped. It's a completely solid mass of cellulose material. So there's no plastics, there's no metal core or anything. It's the design is called a depth media style filter. So we're basically taking the oil and pressing it all the way through the cellulose mass. So it's a totally renewable resource, and each insert will remove about 12 pounds of contamination. So yeah, just kind of comparing surface filtration, which is kind of what's happening with most of the spin-on style filters, versus depth media filtration. So you can see on the top right there, that dense cellulose material that's capturing the particles and oxidation. And you can see the example at the bottom with the many layers that the oil has to pass through. Whereas surface filtration, it kind of just has one chance for the surface to hit the particle to hit the surface. And then that material has one chance to trap the filter, which is susceptible to having holes through it, or the system pumps cycling on and off and kind of pushing particles through. So it's just a lot more of a thorough cleaning process to have that large amount of cellulose filter material. Yeah, just kind of comparing the OEM style filters with the CC Jensen filters. So the 3612 and the 3616s have 6 filters, but from my understanding, it's a duplex dynamic. So you're shifting over from one set to the other. So in terms of operational capacity, you're only running with about 1.5 pounds of kind of capacity in those inserts. They don't have a published capacity on those inserts, but I was just estimating each insert probably holds about 0.5 pound. So 3 inserts, you're getting about 1.5 pounds of holding capacity in those inline filters. And then of course, those are full flow. So you don't have that luxury of kind of running slower. And then so by adding the HDU filter as a kidney loop filter, you're able to dramatically increase both the holding capacity for dirt and then the added ability to remove oxidation. And then also it's a massive increase in terms of filtration efficiency. So yeah, this is kind of a typical used set of filter inserts. You can kind of see there's a massive amount of contamination removed in each of those inserts, along with oxidation. And roughly we're estimating about 2 to 3 filter changes per year. Obviously depends on kind of each engine and how much contamination is being loaded into the loop system. Yeah, just comparing the spinner technology, which some people may be familiar with, and the CC Jensen unit. So it's quite a different technology. The spinners utilize centrifugal separation. I don't know that they're probably not going to be removing the same amount of oxidation. There will be some oxidation removal. We're really targeting the oxidation with the cellulose depth kind of design. And then one issue that we've kind of heard from end users was uneven loading in the centrifuge. So it's kind of like when you get your dryer at home, all of the clothes load to one side and it's boom, 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 boom. So that kind of effect can happen in the centrifuge. And we've heard kind of bad stories of piping breaking apart and that kind of thing due to uneven loading in the centrifuge.
And on the other side, the CC Jensen style, as you saw with the cutaway, is just a much simpler design. The pump and the motor are the only 2 moving parts really in the system, and the contaminants are captured into the media as opposed to spun to external capture. Definitely some benefits with the simplicity over the centrifuge design. It really does come down to the media that we're working with here, and the construction of the C.C. Jensen filter inserts is, that's a closely guarded secret, but a tremendous amount of research and development has gone into the media itself, the selection of the individual cellulose fibers and the means of blending them together. And here you can see zoomed in scanning electron image of a glass fiber type filter media versus the cellulose that C.C. Jensen's using. And in this case, the seeming chaos of the cellulose media is one of its biggest assets, whereas the glass fiber has a very predictable flow path. The surfaces are smooth, and the contaminants can pass through, whereas the cellulose has a very random web, which is great for mechanical filtration, but the cellulose also has a chemical and an active component to it. And the particles, especially below 1 micron, will form bonds with the cellulose. And those bonds tend to increase the holding strength in areas of uneven surface. And so what you end up with all these fragments and tiny fibers and sinews is a lot of surface area for those submicron particles to bond to in the filter media itself. So there's some strong advantages to the natural fibers that are used, and even some regeneration effect on the oil itself, in terms of transferring molecules from the cellulose to essentially restocking depleted additives in the oil. So some active chemistry going on with the cellulose media. One thing to note, that the contamination of the oil can happen not just from being used in service, but it can also happen from residual contamination left over after an oil change. I have an oil pan there. Obviously, it's a much smaller engine, but just to illustrate what can happen in the engine, that if you're just changing out the oil and expecting that to provide you with the protection that you need and rejuvenate all the properties of the oil, it can quickly be degraded just by running over residual contamination in the system. So as the additives deplete, essentially they dedicate themselves to the cause, whether that's suspending particles or attaching to metal surfaces for protection. Those particles the additives will be depleted over time, and they can contribute to, as they get used up, they'll stick to surfaces in the system, and you can see elevated additive levels even after an oil change, because those contaminants are still left behind. So here's an example, and this is common from engines in this industry. So 3 additives that we're looking at here: calcium, zinc, and phosphorus, and looking at the additive level before and after an oil change. And you can see the yellow line there on each of those charts is the reference sample, so that would be new oil. And you would think that after an oil change, your additive levels would be very close to that of new oil. And what we do see is elevated additive levels even after an oil change, and that's indicative of these spent additives being left in the system after an oil change. So the quality of the oil change also has an impact on the longevity of the oil and its ability to do its required task. So there can be quite a difference between a thorough oil change or a quick just dump and refill, and often that can take a lot more work, but the benefit will show up.
Yeah, I think we've thrown a lot of information out there at you guys. We wanted to open it up for some discussion now. I don't know if we can turn on everybody's audio here, and people can have comments or questions. We can kind of open up discussion. And part of what I wanted to do too is going forward is get a lot more feedback from the field, from those of you that are going to operate or already operating these filters, is to absolutely share oil analysis with us. Share pictures of used inserts, share your feedback, positive or negative. So we want to hopefully do webinars in the future where we have a lot more data points to share with you guys.
Okay, we'll see if we can open this up here.
Yeah, guys, you can go ahead and see if you can equip your mics and make just try to say something, see if the audio is coming through here. Maybe you gotta unmute them all.
Yeah.
Oh, sure. Is that just the status of their mics? Yeah, maybe you guys can, if your audio is not working, you could always try to type a question too.
Yeah, you can. There's just there's the chat tab there. So if you're having trouble unmuting or speaking, just put a note in the chat there, and we'll see if we can do that from our side. Yeah, otherwise, I guess maybe just to open some discussion, things that we're still learning and trying to figure out. You know, the extending the oil drains is something that's really interesting. You know, primarily what we're trying to do at this point is just keep the oil clean through the life of the oil cycle. Because a lot of that comes down to scheduling and logistics and all that. But a relevant question is, you know, if all the properties of the oil are still intact at the typical oil drain of 6,000 hours, can we safely extend that? We're interested to know about the reduction of main bearing temperatures, whether, you know, in theory, we know that keeping the oil clean is going to lead to less friction. Less friction means less heat, but we'd love to see some of that data. Same with the sludge, as I mentioned. I'd love to see, you know, on engines with the CJC units on, we'd like to see how at the oil changes if there's a reduction in the overall sludge, and likewise the effect on the wearing components. You know, crankshaft or camshaft inspections, comparing with or without to see those changes. And again, we see this on a lot of other engines, like big marine diesel engines or you know, ocean-going vessels, that sort of thing. But with these CAT engines specifically, we're interested in that. And as Perry mentioned, you know, the conversation prolonging the life of old engines versus proactive protection of new engines. Just some interesting topics of discussion. So yeah, if anybody has a question, fire away. If not, we thank you for your time. And like I said, you will get an email after this with a link to the recording. So feel free to share it or watch it again if you like. Otherwise, yeah, thank you very much for joining us. We hope there was some beneficial material here, and love to hear more from you in the future.
Yeah, and I do have a link in my signature there. So if any of you guys want to schedule a meeting in the future, one-on-one or with our team, then you can certainly click that link in my signature there, and we can schedule a call and we can talk specifically about your operation.
Okay.
Yeah, that's great. I think if no one has questions, then we'll leave it there. And thanks for taking the time to tune in, guys. And if we schedule another one of these calls, we'll certainly be in touch again.
Wait, one question.
Oh, we do have a question.
Thank you.
Yeah. Okay. So we'll let you guys go. Thanks for tuning in and participating with us today.